about the embryology of the spinal cord to show you how the cord rather logically develops from our old friend the neural tube. Then we're going to spend some time talking about the gross structures of the spinal cord, its configuration and so forth, its membranes, and its organization. And that, you see, will sort of set the stage for this coming Thursday when we begin to talk about the actual tracks, the bundles that make up the cord, and what they do. And folks, remember one thing. Sure, we're going at this from the anatomical point of view. But as they say, anatomy qua anatomy is the most boring thing on earth. What is important is what these structures do, what their pathways are, what they carry, and how that produces behavior and cognitive activity. That's what we're in for. That's why we call this functional anatomy. Now, let's talk about the spinal cord, how it's organized, and to do that, we'll use the whiteboard first, so you can get these things in your notes, and then we'll show some slides. Now, the spinal cord develops from neural tube. Now, you remember that originally the neural tube separates itself from the overlying ectoderm. And you have extra neural crest cells up here. And you have these masses of tissue at each segment. These masses are going to become the muscle, the bones, and all the solid substance of the body. Whereas the neural tube, under the influence of the underlying notochord, is going to rapidly develop. And how is it going to develop? It's going to develop by the replication of these cells that make up the wall. And I told you there are only probably several tens of thousands of these primitive cells. We call them neuroblasts. And they're going to become both neuroblasts and glioblasts, and then gradually differentiate into neurons and glia. Now, the notochord is not a silent partner. It's producing a number of inducing substances that are moving up this way. And among those is that wonderful inducer. You can't forget the name. It's so charming. Some of you have heard of it. Sonic Hedgehog. Yes. Isn't that wonderful? Yeah. And this is a gene product that has an interesting effect on these overlying, rapidly replicated cells. Let me show you what it does. I'm just going to draw the neural tube from here on in, and it's going to look like this. In other words, you're going to get more rapid replication down here in an area that we call the basal plate. And you're also going to get rather rapid replication up here, an area that we call the alar plate. And the reason these are of interest to us is because basal plate cells are going to become motor or motor-involved neurons, whereas alar plate cells are going to become sensory-involved neurons. In other words, they're going to receive and handle only sensory-involved information. This little wasp waist area between them, that little, almost, it forms a little valley here, that's known, I'll put it on this side, as the sulcus limitans, the limiting sulcus, the limiting valley, if you will. And that sulcus limitans, we're going to see represented not only the spinal cord level, but in one way or another, all the way up the brain stem, as far as probably the diencephalon. And the role, if you will, of the sulcus limitans is to form a division between presumptive sensory cells and presumptive motor cells. And the way the notochord, working under here and producing these inducers, the way it works is apparently high concentrations of substances like sonic hedgehog tend to favor the production of motor-involved cells. Whereas up here, where the density of these molecules is much less, it appears that lower density of sonic hedgehog favors the production of sensory-involved cells. Now, let's go down and see where you can all see it. So let's go over here. With time, as this replication continues, the wall of the neural tube increases in thickness. And these cells that are replicated so quickly here in a layer that we call either the ependymal or germinating layer. There are many, many terms for it. These cells, after they go through their replication cycle, they move out externally away from the replicated ependymal layer and move into a layer out here. And this becomes the new mantle layer. Mantle layer. In the mantle layer, these cells which have ceased their replication now begin to mature. What do I mean by that? They begin to develop primitive dendrites. And then, of course, they've got to develop a primitive axon. Now, in this spinal cord area, for some reason, the axons all move still further laterally. So I'm going to, see, I can do this. I know you can't do this on your notes, but it makes it a little quicker. The axons all move out here and form a new layer that's known as the marginal layer. So we see the neural tube gradually enlarging, both of course in length and in diameter. And we see the cells in the ependymal layer. After they stop replicating, they migrate outward, laterally, to form a mantle layer where they begin to mature physically. And then as they mature physically, producing dendrites and axons, the axons move out to become this most external layer or marginal layer. And if we look at a mature spinal cord, I'm going to draw a spinal cord, just half of it for. Here's a mature spinal cord. What do we have? Well, we have something like this. What do I say? Remember, this is half. This is the midline here. What's left of the ependymal layer is found in just that single layer of ependymal glial cells around the rudimentary central canal. The mantle layer, which the cells maturing, makes up the gray matter of the spinal cord. By the way, did you ever notice that gray can be spelled in two ways? G-R-E-Y and G-R-A-Y. Think about it for a moment. So this is a change of set for a moment. Think about that G-R-E-Y, G-R-A-Y. Which one gives you, internally, conceptually, the deeper sense of gray? E-Y or A-Y? E-Y. That's right. E-Y feels like a deeper sense of gray. Okay, so, hadn't thought of that before, had you? You learn a lot of this class. So the math layer becomes the gray matter. And the axons, I've told you all, project out in this region. What is this region here? It's the white matter, absolutely. So that is the embryogenesis of spinal cord, and you can see how it relates to the embryological development of the more primitive neural tube. Now let's take this off and begin to talk about the organization of spinal cord. It's a tube, a tubular structure, I should say. It's around 45 centimeters in the male, and maybe a couple centimeters shorter in the female. I'll put a spinal cord on it, just we're looking down on it, and I'm going to accentuate certain features that aren't really quite as obvious in the normal cord. Now, this is going to be the foramen magnum here, where of course it disappears into the skull. So we'll put in something like this. Slight enlargement there. Then it progressively narrows. Another enlargement here. And then it narrows down and ends at a point. We say that the spinal cord is a segmented structure. This doesn't mean that it looks like an earthworm with actual segments. It's actually a continuous tube. But it is functionally segmented by pairs of dorsal roots and pairs of ventral roots. I'll show you those in a moment. And all together, because of the root emergence and projection from the cord, there are, we say, 31 segments which are made up of 8 cervical, 12 thoracic, 5 lumbar, 5 sacral, and usually 1 coccygeal, making up a total of 31 double pairs of roots, 31 segments, we say. And it so happens, as we'll see with the slides in a few minutes, it so happens that each of these groups of roots for each segment supplies just a strip of the skin and the underlying tissues of the body. And you'll see the way it looks. And the neurologist, by knowing the distribution, say, oh, C6 is here, and T4 is here, and so forth, if he tests you with a pin or a wisp of cotton, and you have, let's say, no sensation at all here, or too much sensation, they call that hyperesthesia, don't worry about that now, he can begin to make deductions as to where the trouble, the lesion may be, in the nerve root coming to that, or in the spinal cord. So we'll talk about that in a moment. Now, what are these enlargements? Well, in the lower part of the cervical and projecting onto the thoracic, we usually say about, C4 to T1 or so, is what we call the lumbar, beg your pardon, that's dirty, the cervical enlargement. Let me see, T1, yeah. This is the cervical enlargement. And all it means is that the parts of the spinal cord are somewhat fatter here, somewhat larger, because this is where all the connections are with the arm and the forearm and, of course, the hands and fingers. And it takes more cells and more fibers So the cord itself is slightly enlarged, hence the cervical enlargement. And then down here, usually from about L2 or L3 to S1, let's say L2 to S1, is what we call the lumbosacral enlargement. For the same general reason that is there, we're concerned with the enhanced number of cells and fibers that are necessary to control the legs, the feet, and the toes. You can understand that. Notice that the thoracic cord here is appreciably thinner, which indeed it is. We're going to look in a few moments at successive levels to understand it. We're going to learn how to recognize the various levels at which the spinal cord operates. So, having put that on the board, now what I'm going to do is, I assume most of you have gotten this, I'm going to take this off, leave the rough sketch of the cord on, and just talk about how the cord is suspended within the vertebral canal. The vertebrae, you have a body of the vertebra here, and then you have a lateral process, and you have articular process that I won't put on, a posterior process. And you have here a canal, and it's in this canal that the spinal cord is suspended. Now the cord itself, just like brain tissue, the cord is closely covered by pia, which sticks very closely to its surface. Then outside of the cord, there is a meningeal, a dural layer like this. This is dura. So we'll find that the cord is in a kind of dural sac. The arachnoid, of course, as you know, is just inside the dura, and it communicates here, as in the brain, by these little wisp-like arachnoidal processes that connects the layer of arachnoid, which is attached to the dura, connects that to the pia, and you have a subarachnoid space all through here. Now the cord itself, we found, by the time we're born, the cord has relatively shortened. Remember, we'll show you a slide of that. The cord has relatively shortened and terminates around the L1, L2 interface between lumbar 1 and lumbar 2. And then from that point on, this sac is filled with the nerve roots that are finding their way out. They originally were way down here, now they've been pulled up. And that root, remember, that group of roots we called, remember the horse's tail, the cauda equina? The cauda equina is the mass of roots that are leaving the lower part of the spinal cord to find their way out to their own particular vertebral foramina or hole, which is how they gain egress and access to the spinal cord. But let's finish up with the membranes first. I'm just going to remove this just for clarity's sake. Right? The very most caudal part of the spinal cord is like a little cone. And it's called, for that reason, the conus medullaris, or medullary cone. The pia that has covered the spinal cord so intimately down to here, the pia now is concentrated into a single firm little thread. And that thread continues down through this dural sac, through the subarachnoid space. It comes down to the very bottom, the lowermost part of the dural sac, which is still only at about S2. And then the sac itself conglomerates over this little peel wire, and together they go down to the very bottom of the coccyx where they attach to bone. Now this process that is originally just congealed pia and then gets its little dural addition too, that is known by everybody as the phylum terminale, or the terminal wire, if you will, the terminal hawser. And you know, it's quite critical. What it does is, it holds the spinal cord down at the bottom and attaches it to bone and keeps the cord from moving around and swaying as we walk and move and so forth. It's a curious thing that in trauma, in certain kinds of lower spinal trauma, it is broken or torn, and then, believe it or not, it's almost impossible to cure. There was, I believe a faculty member up on the UC Berkeley campus who had an accident and who broke his phylum terminale. From that time on, he had a terrible problem with incontinence and pain and all that kind of thing, simply because the spinal cord could not be tethered down at its most caudal end by that phylum terminale. Now the cord is also held by a number of projections from the side. They are a combination of pia and arachnoid, and they get a little covering of dura as they come out here, and they attach to the dura and the overlying bony wall of the vertebra. And they look like little triangular expansions, which is just what they are, of this membranous tissue, and together they make up on each side, they make up a system that we call the denticulate ligament. Between the denticulate ligament, giving lateral stability to the spinal cord, and the phylum terminale, giving caudal or terminal attachment to the cord is suspended in this little subarachnoid space just under the dura, and that's the way that it's maintained. So I would like you to remember this arrangement for stabilization of the spinal cord. It's very useful to know. Here they are. Now, may I take this off? Do most of you have most of this material? Now, there are a couple other things I want to show you, and then we'll go to the slides. See how we're doing on time. A little bit now about the parts of the spinal cord itself. Here we are. Cross-section of the spinal cord, anywhere. First, a word about terminology. I told you terminology, especially in neuroanatomy, is terrible. The two words, dorsal and posterior, are synonyms. So we can say dorsal equals posterior. And in the same way, ventral equals anterior. Dorsal, of course, from dorsum means toward the back, and ventral from venter means toward the stomach side of things. and then say they are synonyms here. The reason that I mention that is because in the terminology that we're going to use, both are used, both are acceptable, and so forth. We first know that the spinal cord is made up of gray matter and spinal cord, white matter. Gray matter and white matter. The gray matter is made up of a dorsal or posterior horn, a ventral or anterior horn, and, not surprisingly, an intermediate area. And we're going to find that these, of course, are the neuron-rich, the cell-rich parts of the spinal cord. Just a few words about how the gray matter that we're talking about now is organized. One can see, even with a simple missile stain, and one sees ever so much more clearly with a stain, say, with the Golgi, or where one micro-inject cells to visualize them, or use HRP or whatever. One can see that there are many different kinds of cells with definite levels, patterns of organization. And we used to have names for these, believe it or not. We call the area up here the area don't worry about this. The area gelatinosa, because it looked so gelatinous because the cells were so small. And the area underneath that we call the area spongiosa, because it, I guess, looked to somebody like a sponge. And we had interneuronal pools and motor neurons down here and so forth. I remember this very well, in 1951, a Swedish investigator named Rexed, don't have to worry about it, just a little bit of interesting related history I have to be involved with in a negative way. Bror Rexed sent a manuscript to the Journal of Comparative Neurology, which was the reigning neuroanatomical journal of time. And in that he proposed that you can organize the gray matter, the cells of the gray matter of the spinal cord, into 10 layers or laminae, almost like the layers in cerebral cortex. He furthermore claimed that they were psychologically different, and that from what little he could gather from the literature, they also were physiologically different. Now, believe it or not, I was just a postdoc. The editor of the JCN was in the same building, a fellow named Van Bonin, said, Scheibel, what do you think of this manuscript? So I read the manuscript, and I told him I didn't think there was anything in it. He therefore promptly published it, and it became the stock in trade of spinal neuroanatomy. Rexed was right, of course, which simply proves that when an editor asks you a question, the best thing to do is to say nothing. So the Rexed laminae, 10 layers in the spinal cord, represent today very modern thinking about organization of the gray matter. All that I'm going to ask you to remember is that the laminae up here, the first one is very thin, these are involved with sensory influx coming into the spinal cord. You have neurons here that are involved primarily in what we call relationship. They are interneurons. They handle both motor and sensory inputs and send them to various other levels of the spinal cord. We'll talk about those briefly. And down here, are actually making up layer 9, are a group of motor neurons, motor neuron pools, that actually send their axons out to the muscles to be innervated. It's from down here that the spinal cord does its actual work. So that's sort of a brief look at the gray matter of the spinal cord. Now what about the white matter? The white matter is broken up into fiber masses. Each fiber mass tends to be true to itself. You've all seen birds sitting on telephone wires. You have one group, they hear all the doves, they hear all the sparrows, they hear all the ravens. You know, birds of a feather flock together. The fibers of the nervous system are just the same way. They segregate by function. And we're going to learn what a few of these are, just give us appreciation. But in order to do that, I must remind you that a large white matter bundle here, which is known as a funiculus, it's essentially a large bundle. This is known as the posterior or dorsal funiculus. This is known as the lateral funiculus. And what do you think this area down here is known as? It's the ventral or anterior funiculus. Now those funiculi are made up of specific tracts or fasciculi. Isn't that disgusting? Fasciculus or fasciculi. And it is the fasciculi making up the funiculi which carry modes of information which are specific to the fasciculus we're dealing with. And we're going to learn, as I say, 3 or 4 of these major bundles traveling in the posterior funiculus, the lateral funiculus, the anterior funiculus. You see this indentation or sulcus here, and this septum. On the dorsal or posterior side, that separates the 2 halves of the cord. That's known to everybody, for obvious reasons, as the dorsal or posterior medial sulcus and septum. And if that's true, it doesn't take much to realize that this must be known as the anterior medial. In this case, they call it a fissure because it's a little wider, but it's the same thing. Fissure and septum. Now, right here, where the dorsal horn comes closest to the surface of the cord, there's a little indentation because that's where the dorsal root fibers are entering. And that is known, not surprisingly, as the dorsal or posterolateral sulcus. So let's see if we're running out of space here. Let's put it over here. The dorsal or posterolateral sulcus. Let's say posterolateral sulcus. And for the same reason, you have a little indentation here where the motor neuron axons are leaving the spinal cord. And we call that the anterolateral sulcus. Now those are really the major just gross structures in the cord. The only other thing that I will add to your troubles and woes is that starting in the uppermost thoracic, but primarily in the cervical, the posterior funiculus, or posterior column as it's often called, is divided by a little septum, a so-called posterior intermediolateral septum. Intermediolateral, meaning it's not quite medial, it's not quite lateral, it's in between. And that little septum, as we'll see, divides the fibers of the posterior column of funiculus into two types. They're carrying the same kind of information, but it's coming from different parts of the body. Don't worry about that now. It will become obvious to us when we talk about it shortly. Now, the last thing that I want to do for you in this portion of the talk is to remind you how these systems are organized. And after that, of course, we'll take a little break and we'll go to slides. Here is half the spinal cord, dorsal horn, ventral horn, central canal. I told you, each segment of spinal cord is characterized by having a pair of these dorsal or posterior roots and a pair of ventral or anterior roots. The dorsal roots, they all have a dorsal root ganglion or posterior root ganglion. I'll simply call it DRG, that's short for, in this case, dorsal root ganglion. And how are these now? Well, these are filled with our old friends, the pseudo-unipolar cells. Remember those? They start out as bipolars, and the axons come down, and the axon fuses for a short distance, and then you have a peripheral process and a central process. So let me put just one in here. Here's the peripheral process going out, let's say, to the surface of the body, maybe. And here is the central process coming in, and some of the fibers may go up here, and some may make synaptic connections and so forth. This is your dorsal root. You have a pair at every segment, as I say. And what about the ventral root? Well, the ventral root comes off here. Let's put a motor neuron in. Let's put its axon coming out. And just past the dorsal root ganglion, they fuse and become a spinal nerve and run together for a short time before they begin to break up to innervate various parts of the body. So we have pairs of dorsal roots, pairs of ventral roots, the dorsal root ganglion, of course, the ventral root here, the fibers from it join just peripheral, just distal to this area, and form a mixed spinal nerve, which then continues out and then gives branches to various places. How about a little law now? You know, when in doubt, invoke a law. When in doubt, make a law. There was an old humorist back in the early part of the 20th century. How many of you here have heard the name Will Rogers? Few of you have. Great Western humorist. Everybody loved him. Had a wonderful humor. He used to say about the people in Congress. He said, you know, he didn't think too much of them. He says they're all a bunch of comedians, basically. He says every time they make a law, it's a joke. And every time they make a joke, it's a law. So you see, we're invoking a law now that doesn't quite hold, but it's good enough. And it's known as the law of Bell and Legendre. The law of Bell and Legendre states that every fiber in the dorsal or posterior root is carrying sensory information in to the spinal cord. And every fiber in the anterior root is carrying motor information out to the muscles of periphery. That still holds pretty well, even though there may be 5 or 10% of sensory fibers that somehow sneak in. They get lost, they sneak in via the ventral root. But nobody talks about them. You know, those are sort of like the poor relation you like to forget about. So in general, the Bell and Legendre law is okay for distribution of sensory and motor fibers. Now what I'd like to do is give you about 7 minutes We'll take a break, go to the bathroom or whatever. Let's start again at 10:15.